Alright, as I usually do with these test equipment videos, I'm going to start out looking at Chuck Penson's excellent book, Heathkit Test Equipment Products. Flipping to the section on digital frequency counters and multimeters. Heathkit's first digital product and also their first frequency counter was the model IB-1100, which I have a video on already. A 15 megahertz frequency counter. It was introduced in 1970 and it sold for considerable price, about $220 at that time. A good chunk of change, although you wouldn't have been able to touch it with a commercial product anywhere near that price at that time. Heathkit was delivering value for money for hobbyists and lower end laboratories and educational institutions. They needed something similar but not quite so expensive. So they came out with the IB-1100, came out 2 years after the IB-101, and it was twice as good in many ways. It was a 30 megahertz frequency counter that brought it a little bit more into the mainstream of lower end counters, and even today there's a lot of frequency counters in this approximate frequency range still made and available. The IB-1100, which is the subject of this video, came out in 1972 and was made through 1975. The book says the 5-digit 30 megahertz IB-1100 was designed in an effort to maintain a low-priced counter in the product line. It was sold side by side with the IB-102 scaler, which had been produced or reduced to just $99 at that time. The combination bought you a 175 megahertz counter for a total of about $285, cheaper per megahertz and faster than any other Heathkit counter frequency range. Of course, in the same year, Heathkit came out with the IB-1101, which was like an IB-101 externally and feature-wise, except it went up to 100 megahertz. And that was carried also through 1975, so it was running side by side with the 1100 as a much more capable unit. And I also have a video on that. But I'm going to focus on the IB-1100 in this video. Okay, here's the artifact. Not a bad little frequency counter, decent look to it. This came to me from an eBay seller who had been using it in his own lab and said it was working fine, but he was just not using it anymore and decided to downsize a bit. It really has the same controls on it that more expensive counters of the same period, such as the IB-1101 and 1102, which just had an on-off switch and a kilohertz megahertz switch. But here, instead of nice rocker switches, they're, cheaper slide switches. It only has 5 digits of Nixie tube display in this area. It doesn't have any on-screen indicators for gate. You just don't have that information. It's probably the least important indication on a counter. It has a separate lamp for overrange and no indication for kilohertz or megahertz. A single BNC input. On the bottom there are 4 feet. These are not the soft bump-on ones, they're hard plastic feet, so a little cheaper there. However, the front ones do include kickstands, so you can prop it up. It doesn't have a carrying handle that props it up, it's just these little kickstands. And there are 2 holes here for screwdriver access to input sensitivity potentiometers that are obviously just on the circuit board up there, and I can expect that we'll see that this BNC goes immediately to the front of a circuit board and there's going to be a fairly simple circuit there for input signal conditioning, and sensitivity will be part of that. Going around the back, it's pretty plain. It has a lot of similarity to some of the details on the rear of the IB-1100 that I already have a video on, such as this type of test point output, just an insulated bolt going through the panel, which you can clip onto or touch a test lead to. And then there's a test point level adjust and a time base oscillator adjust screwdriver axis. And there's this screw here with an insulator on it, and I'm going to guess that when we open this up, we'll find that that's where the voltage regulator is, and it needs to have its mounting bolt insulated from the chassis. Unlike the more expensive counters in this series, it just has a grommet with the strain relief with the power cord going through it. You cannot unplug the power cord on this one. The rear end. I've cleaned the front up as much as I can. It wasn't too bad, but there were some areas that needed some attention. Taking it apart involves removing a lot of screws. 1, 2, 3, 4, 5, 6 sheet metal screws on the back, and then several screws through the flanges here, and at least 4 of these go into the circuit board mounting studs. So you actually have to, by removing these screws to get the case off, you need to necessarily or consequently make the circuit board loose from the chassis. That's not the greatest design. Note that these two and these two screws are machine screws because they go into threaded holes on the spacers for the circuit board, whereas these two holes towards the rear are sheet metal screws, or at least one of them is. Let's see. Nope, that's right, it's only the one of them. This one here is also a machine screw. This one here is just a sheet metal screw. That's confusing, huh? They could have done that better too. And of course these are all sheet metal screws in the back, so we end up with a pile of screws. Now interestingly, this screw here, at least the way this one came, is a black screw for no apparent reason. And I'm not sure that's what was originally there. That, I believe, does help secure the rear of the circuit board, but I'm not sure that's what Heathkit originally had. And I have a leftover machine screw of a different length than these others, and it may be appropriate for putting in here instead of that black one. 12 screws have to be removed to get this case off. Alright. So we have Amperex Nixie tubes in here. They're not the same model that most of the other Heathkit stuff from this vintage we're using. And we have better sockets on here. Interestingly enough, it's a cheaper meter, but instead of those Molex sockets, it has more what you'd expect. And there's a bunch of Fairchild chips in the first row. I'm sure what we'll find here is, here's the set of ICs for the counter that drives the 5 display tubes, the Nixies. There are 4 ICs of the same kind here, which are probably the counters. And then there's a additional one here, and some more. Actually, yeah, there's 6 more ICs here that are all the same kind as these. I've already tested it and it works perfectly the way it is, but I always change out the power supply capacitors on things this old, and just put an order into DigiKey and get the closest equivalents that I can find. But otherwise it looks nice and clean. Build quality looks pretty good. I think the solder jobs are probably just fine. So not much to do with this restoration wise. Even the case is clean. I don't need to paint it or anything. There are these 2 larger electrolytics and then a couple of radial ones down here and here. And I have those caps laid out here, all purchased from DigiKey. The drag on this one is that there's no bottom access to the circuit board without taking the whole stinking board out of the chassis. 1, 2, 3, 4, 5 screws anyway. And probably it can be slid out of there, but I also have to detach a couple of wires and a regulator or a transistor on the chassis. It won't be fun. I think I'll save that for another day. Alright, I've replaced 1, 2, 3 axial electrolytics and 2 radial electrolytics. Wasn't easy to work on this. They did not make it easy to get access to the back of the circuit board once it was all assembled. Alright, just a little bit of a functional test before I put it all back together again. That's a 1 megahertz signal coming in the 1 megahertz range setting. If I put it back to kilohertz, it'll overrange, which it did. And I'll put it back to 1 kilohertz. Boom, there we go. That's working. Good. There's some cheapness here. It still has the cast metal bezel, but unlike the higher class counters and meters in this series, it holds on the front with screws right through the front plastic window, and it doesn't have that middle strip that's part of the bezel. So just a little less expensive in the manufacturing details here. Also, it doesn't have the 2-part case, nor does it have the handle. Very simple. And I briefly thought that maybe the person who built this kit just decided, hey, nuts with those Molex strips, I'm going to go and buy some sockets and put them in. But no, the Heathkit assembly manual does show that this is what it came with. Another thing that's sort of odd about this, all of the other meters and counters in this series use the same kind of National and Burroughs. I think probably Burroughs originally, with National being a second source, but the same type model of Nixie tubes. And this one instead uses some tubes by Amphenol, which are not the same. They're actually a bit larger than the ones on the nicer equipment. Go figure. Maybe they had a bunch of these and had to use them up. Don't know. Just a quick overview of what's what on the circuit board. So all of the power supply components are back in this area here. Filter capacitors here. couple of transistors, power transistor on the back panel for heat sinking, and various diodes down there on the circuit board. The clock is on these components here. Starting about here, there's the crystal. Here's a quad NAND gate that's used for the gates that are part of the crystal oscillator circuit. And I realized when I changed out the capacitors, I didn't change this one. These chips here are all part of the overrange logic. These 6 ICs here are the 6 decade counters that divide down the clock to get the gate, the transfer, and the reset signals. Then all of these ICs here are part of the counter, latch, and display driver IC set. And then finally, all the discrete parts down here are part of the front end circuit that conditions the input signal to become a TTL level logic signal. Unlike the more expensive equipment in this series, it does not use an unpluggable line cord. It just uses the less expensive method of bringing a cord in through a strain relief. The hot lead goes to the fuse, the other side of which goes through the red wire up to the power switch. Wire goes back to one side of the transformer, and that's where the neutral side of the line cord goes. And by changing those jumpers, there and there, it can be wired for 240 volts AC. It's currently wired for 120. Another thing to point out is that on the other meters counters in this series, Heathkit used either an incandescent or a neon bulb into a little lamp housing that would both hold the lamp and kind of focus or direct its light forward. And in this case, the cost-cutting move of just having a hole in the chassis with a neon bulb light on its side on the circuit board is used. Actually, I think this one lights up better than the ones on the more expensive ones. And that's because they just have a tinted area of the window there instead of letters like over or kilohertz or megahertz or something, which always illuminates more brightly in the middle and not so much towards the ends, sometimes making those letters a little hard to read. Here they just wrote over range on the window and then just have the light shining through. You get a nice bright round image. Kind of wish they'd done this type of thing with the other models. That little foam pad on the circuit board next to the crystal adjustment capacitor, that's that tubular shape. That's probably the high voltage foil on the circuit board that's running from the power supply way up to the front where the Nixie tubes are. So yeah, you wouldn't want to stick a metal screwdriver through there into the trim cap and then short it against that circuit board foil. That would be a big zap, and the magic smoke would be released. Alright, let's see if this guy works. I have the input connected to my signal generator, which is currently set to 4 volts peak to peak, sine wave, 1 hertz. The counter is in the 1 kilohertz mode. And since it has 5 digits of resolution, I should be able to register a 1 hertz input. So let's turn this guy on. Let it zero out. Nice clear display, very nice looking display. Turn the signal generator on, and we get a reading of 1. So this would be 1 kilohertz over here. It's kilohertz, kilohertz, decimal point, and then down to here. So it's reading 1 hertz. Let's go up to 10 hertz. Takes a couple seconds to gate its way up there. One thing I don't like about these Amperex Nixie tubes is that it's more apparent of the depth. The one seems to get mispositioned unless you're looking absolutely straight at it. The ones they used on the other products in this Heathkit line, it's not so apparent when that happens. Alright, let's go to 5, 15 hertz. $145 hertz. $645 hertz. Let's go into the kilohertz range. 1.26 kilohertz. 1.26. The decimal point is not super visible there, is it? But it is there. Just not the best design for the Nixie tube decimal point that I've ever seen. It almost disappears. I think the problem is it's a little too close to the numbers, to the digits. Let's go up an order of magnitude. 12.345 kilohertz. 12.345, right on the money. And it's interesting that the way that these Amperex Nixies are designed, it appears that the digits go further back according to the numerical value. So 1 is very close to the front, 2 is behind, 3 is further back, 4, 5. I should check to see the least significant digit to see how that moves around. I'll go to 0. So 0 is further back than 1. 1 moves way to the front. 2 is further back. 4, well, it's right on the money. There are 3 is further back. 4, let it catch up. It's right on the hairy edge. 4 is further back than the 3. 5, let it catch up. That's further back than 4. Wait a couple seconds. The 6 is further back yet. 7, I'm not really sure where that is relative to the 7 moves forward. And 8 is forward again. And 9 is so it's like 1, 2, 3, 4, 5 are all in order, then they start staggering around and moving generally more towards the front. Okay, let me put that back to a 5. Now if I go to 92, that should be a 2 in the most significant, a 3, a 4, 5, 6, 7, 82.345, showing 4, 9. Now I just went to 102, 102.345 kilohertz, and we have the very obvious over indication here. Pretty easy to see, although if you're way off to the side it's a little harder. So because of the way the counter works, it still shows what remains. The 1 is over here for the 102. It just can't display it by indicating over unless you've just come in with a really high number. If you've kind of crept up to it from an area that it can display, suddenly it reads over, you can assume that there is a 1 over here and still read the rest, the least or less significant digits. So let's switch over to megahertz now. So 102, we don't have the ability to show any lower resolution than that. It's currently at 0.102 megahertz. So I'm going to go up to, let's see, 12.345 megahertz. Right on the money. I'm going to take it up to 22. Right on the money. And my generator won't go up beyond 25, which is what it's displaying there. Although the counter can go up to at least 30 and maybe a bit higher. So, this guy is working perfectly. Okay, here's the beauty shot. Alright, let's take a look at the Heathkit manual. This is not an original Heathkit manual, it's one of the high quality reproduction Heathkit manuals produced by manualman.com. With my own binding on it. They don't do wire binding. They use plastic comb binding usually. So we start out as usual with a picture of the product and the table of contents. An introduction. The Heathkit model IB-1100 frequency counter is a compact, lightweight, easy-to-use, solid-state frequency counter which is capable of accurate measurements from 1 Hz to over 30 MHz. One of the many features that make it so convenient and easy to operate is the simple, straightforward design of the front panel. A power switch and a megahertz-kilohertz time-based switch are the only controls. The input attenuator required in some counters has been eliminated by an especially designed input protection circuit which assures minimum loading to the circuit under test. 5 display tubes provide a bright readout at a glance, and a neon lamp is used as an overrange indicator. Excellent accuracy is ensured by modern digital design and a specially selected crystal for control of the time-base oscillator. This crystal-controlled clock approaches the performance characteristics of a temperature-compensated crystal oscillator. Additional features include the rugged and compact cabinet design, the detachable test cable, that would be via the BNC. That's kind of like bragging about something that everybody has. The front feet equipped with snap-down wire bails so the front panel may be elevated for different viewing angle. Exceptional accuracy, compact design, and the simplified operating controls combine to make this counter an invaluable tool for the engineer, technician, or hobbyist. Then we have the parts list, which spans about 2.5 pages. And then the large fold-out parts identification drawing. The usual step-by-step assembly primer. Then we get into the circuit board assembly. As I've mentioned elsewhere in this video, this is the only Heathkit in this series that I've seen which uses regular IC sockets instead of the do-it-yourself Molex pin sockets, which are kludgy, but they do work. And this is the lowest product, the lowest end product in the series, so it seems odd that it should be the one that gets regular IC sockets. So we install all of those, well, most of them, the ones in a big part of the circuit board. We just install the Nixie tube sockets and a bunch of resistors that service those, the Nixie tubes and the decimal point. Then we're up in the power supply section. It's a little odd because this circuit board would normally be viewed rotated 90 degrees to the left. I think that their diagram could be a little initially confusing, but it confused me slightly. And then we get down to other components in the same area. This was ICs and resistors. This is transistors and diodes. Still up in the same neck of the woods, we're installing the ICs. And then we install the ICs everywhere else. Then we're down in the front end circuit, or the input circuit, with potentiometers and resistors and diodes. Then in the same section we're putting in all the transistors here. Same basic area, we're putting in capacitors. Oh yeah, they do change the orientation of the board. I think most other Heathkits I've seen, they always show the board in the same orientation for the thumbnail view, and here they're rotating it around. That probably caused some people a little moment. Anyway, so now we're in the power supply crystal oscillator section, really just putting in the components. Well, there is a power supply component being put in there. So the crystal, some transistors, trim pot, trim capacitor, putting in a wire, more capacitors, and the power transistor, soldering wires to the circuit board. Chassis assembly, putting the BNC connector and the two front panel switches on, screwing the wire bails and feet to the bottom of the case, a ground lug, and the test point, insulated test point assembly. Oh, and the fuse holder. Mounting the power transformer, putting the spacers or standoffs on the circuit board, wiring the power transformer to the circuit board, putting in the remaining screws that hold the circuit board to the chassis. And this is where you put in that piece of foam rubber along the bottom edge of the window cut out in the chassis. Identification of various pieces of hardware and other points that were used in an earlier step, because this would be referenced from that. a high voltage warning diagram, just an overall view of what things look like up to this point in the assembly, connecting the wiring to the range switch and power switch, mounting the power transistor to the rear of the chassis, assembling the strain relief for the power cord coming in the rear of the chassis, how to wire up the power transformer for 120 volts or 240 volts. And it's also something I often forget to mention that Heathkit was pretty good about including diagrams that are essentially rulers in any page that has something to do with cutting wires to length. So it's right there, you don't need to have your own ruler. Putting on the Heathkit label, which gets put in different places depending on how you've wired the power transformer. Mounting the front panel and the front panel bezel to the chassis. Assembling the test cable with its alligator clips at the end. Then the initial checkout, a couple pages of that. Resistance checks, voltage checks, display checks. Final assembly, basically sliding the outer case over the rest of the chassis. There's a figure there for how to connect up the included test cable for sensitivity and test point adjustments. It's basically reading its own output from the rear panel and coming around to the front so you can display what it's picking up back there. And then how to adjust the test point, trim potentiometer, and the time base oscillator adjustment, and illustrations for hooking things up for a couple different ways that are described in the manual. Then the calibration procedure without instruments, and with instruments. Then we go straight into the operation instructions. Mentions that the maximum input voltage needs to be derated. It's upwards of 150 volts all the way up to 100 kilohertz, and at that point it's dropping at a pretty constant rate. So by the time you get to 1 megahertz, it's only 102 volts maximum input. By the time you get to 10 megahertz, it's about 54 volts maximum. And at the rated maximum of 30 megahertz, you can put in about 24.7 volts safely without damaging anything. In case of difficulty, troubleshooting chart over a couple of pages, some important wave shapes, and it rolls over to the next page. Specifications. Frequency range 1 Hz to over 30 megahertz. Accuracy is plus or minus 1 digit, plus or minus time-based stability. Sensitivity after a 30-minute warm-up is 100 millivolts RMS typical, 250 millivolts RMS maximum. The gate time is either 1 millisecond or 1 second with automatic reset. Input impedance is 1 mega ohm shunted by less than 20 picofarads. The maximum input voltage I've already mentioned. It's described a different way here. Time-based frequency is 1 megahertz. Time-based stability. Front panel indications. Rear panel test points and adjustments. Front panel controls. Ambient temperature range. Power requirements, dimensions, and its overall weight at about 4 pounds. Circuit description. There's a fold-out with some timing diagrams, which goes along with the circuit description, talking about the input circuit, followed by the first decade counter, which is made out of discrete flip-flops. The second, third, fourth, and fifth decade counters, the overrange detection, readout and memory latches, power supply, a block diagram, circuit board X-ray views. This is from the foil side, and this is from the component side. Circuit board voltage charts. Heathkit always liked to do this, assuming that the people building the kits didn't have access to much in the way of other test equipment. You know, they assumed you don't have an oscilloscope, for example. So they tried to do as much as they could, assuming that the person just had a high impedance voltmeter. You couldn't use an old Simpson VOM on this, it wouldn't work. But if you had a high impedance voltmeter of some kind, a VTVM or a digital voltmeter or a FET front end analog voltmeter, any of those would work. And you probe around various points, and with the input in a certain state and switches in a certain state, you should read pretty close to all these voltages that are pointed out. A few more points that are easier seen from the component side. And then a chassis photograph where they have a mistake. They mark this as Q11. This is the power transistor on the back panel. Should be Q12, not Q11. My highly marked up transistor identification chart. I always go through these before I do my final documentation package, which is always available for download. I try to identify modern suitable replacements for all the semiconductors, so I have a lot of notes about that in here. Continuing on the next page, including the Nixie tube pinout, then the diode identification chart with some more notes of mine, the integrated circuit pinout diagrams. They call it circuit base diagrams. It's dumb terminology. Circuit board functional areas. So looking at it from the front, you've got the input circuit, the Schmidt trigger circuit, which is part of the input circuit, the overrange. This isn't overrange detection, it's just overrange neon driving circuit, the counters, latches, display drivers, Nixie tubes, the dividers for the time base, miscellaneous logic including overrange, reset and transfer signal generation, the clock oscillator, which also includes a little bit of another IC, part of IC21 is used by this circuit as well, and then your power supply circuit. And we go to the fold-out diagram for the schematic. Probably one of the worst Heathkit schematics I've ever seen in terms of just how badly implemented it is. When I redraw it, it'll be way, way, way better. And then finally, a form for ordering replacement parts from Heathkit. Not like that can happen anymore. Alright, let's take a look at the schematic for the IB-1100. The contemporaneous, somewhat higher end frequency counter, the IB-1101, is something I've covered in another video in considerable detail. And as I've studied this schematic, it turns out that the IB-1100 and the IB-1101 are almost exactly the same circuit design. There's just a few things left off of the 1100 that the 1101 had to make it perform slightly better. And it has a couple features that are missing, but those are fairly minor features, like an external frequency reference input. So it feels a little redundant to me to make an in-depth circuit description of the IB-1100 when I've essentially done it already with the 1101. So I'm going to go over this in broader strokes, and then anybody who wants to get more details, just take a look at my video for the IB-1101 and look at the schematic circuit theory section. One place where the 1100 economizes is the power supply. It's very similar in that it has two different voltages, one for the analog section and one for the logic section. That's the same, and an additional power supply for the Nixie tubes to get the high voltage, but they're done differently. For example, the 5 volt higher current regulated power supply that produces, again, 5 volts for all the TTL logic was done with a 3-terminal voltage regulator IC on the 1101. But on the 1100, it's just doing it with a Darlington transistor. And it doesn't even have its own voltage reference, which you'd normally expect. It steals a reference from the 15.5 volt analog power supply, which does have a Zener voltage reference. So let's start with that one. So we have a center tap transformer. One side of all these transformers is connected to circuit ground. The center tap of this winding, center tap of that winding, and one side of this simple winding. You've got a full wave rectifier comprised of 2 diodes, and that's possible because of the center tap going to ground. You've got a filter capacitor. You have a voltage reference comprised of this Zener diode, 16.1 volts, with a current limiting resistor from the raw filtered power here, so that ends up producing 16.1 volts here, and there's a small filter capacitor across it for stabilization. That 16.1 volts is applied to the base of this power transistor, and when you subtract the base to emitter voltage drop of 0.6 volts, you get 15.5 volts, which is exactly what Heathkit says it should be. Now, for the logic power supply, we have the same kind of thing, a full wave rectifier using the 2 diodes, and it's full wave because of the center tap transformer. Filter capacitor again, this time a Darlington transistor, a smaller transistor, and a power transistor. Where is the reference voltage coming from? Normally you'd expect to see a Zener diode here, just like there was up here. But there's already this regulated, well, I still hesitate to call it regulated, but voltage referenced, certainly, 15.5 volt supply there. And there's a 794 resistor and a 550 ohm resistor making a resistor voltage divider to ground. And if you do the math, that comes out to 6.3 volts here. And these are 1% resistors. So with the 15.5 and divided down to 6.3, and with the 1% tolerances on here, you come pretty close to 6.3 volts. So that's used instead of what you might normally have, a 6.3 volt Zener here. So you still have that. You drop 0.6 volts for this junction, drop 0.6 volts for this junction, and you end up with almost exactly 5 volts. It's more like 5.1 volt. But that's close enough for the TTL. So this is, again, voltage reference. There's no feedback, really. So it'll work quite well for most situations, and it's less expensive than a 3-terminal voltage regulator. Finally, you've got just a half-wave rectifier off of this higher voltage winding, and that isn't filtered or anything. On the IB-1101, there's a filter capacitor to ground, and some of the other products use a Villard doubler, where it actually goes through a series capacitor and then a diode to ground, and that produces a pulsing DC waveform. And that's all that's really needed to make the Nixie tubes work. They're saying it's roughly 100 volts, and that'll be an average reading, because if you connect a DC voltmeter to a half-wave signal, it's just going to average the voltage over the entire cycle of the AC power. I imagine we're going to find it's more like 170 volts or something RMS. I haven't measured the winding voltages yet. So that's how the power supplies are developed. The gate and the time base is developed exactly like the IB-1100. It has a 2-inverter oscillator with a crystal, 1 megahertz. That's very common. I think almost every frequency counter I've looked at uses a 1 megahertz crystal, and for logical reasons. Now the way they drew the schematic is stupid. It makes it overly complicated, but it's really just the classic crystal oscillator using 2 inverters. Now they show 2 AND gates or NAND gates here with one input apparently disconnected. On the IB-1100, these inputs are tied high, but on TTL, if you don't ground or otherwise drive an input, it tends to float high in a fairly reliable way, so they obviously got away with just leaving them floating. If when I do further study of this, I learn that they're actually tied high instead of left unconnected, I'll mention it somewhere. And then the resistors and capacitors around here are just to stabilize it and make the crystal work and start oscillating better, that type of thing. So you end up with a 1 megahertz signal here, and it's buffered by yet another inverter made out of a NAND gate with one input unused. The output of that is voltage divided down. The lower half is the test point level adjust potentiometer, and that's brought out to a connector on the back panel. That's your test point output, which is used during setup of the front end circuit up here where the sensitivity needs to be adjusted. So there's an iterative process that you go through using the manual to set one thing, then set the other, then go back and set the first thing, then set the other again, until you end up with no changes in the signals. So you have a 1 megahertz signal here. And then you have 1, 2, 3, 4, 5, 6 decade counters. And these are actually 4 flip-flops inside wired up in such a way as to divide by 10 while producing the ABCD signals for a BCD numerical data in the BCD format. But in this series of decade counters, those ABCD outputs are not being used. So what you really just have is the first flip-flop divides the input signal by 2, and then its output is fed back in to the input for the other 3 flip-flops that are wired up to divide by 5. And with the divide by 2 followed by the divide by 5, you get a divide by 10. So this signal coming out is 100 kilohertz. Same thing happens with another IC, 10 kilohertz, another division, 1 kilohertz, another division, 100 hertz, another division, 10 hertz, and one more division, 1 hertz. So you go all the way from 1 megahertz to 1 hertz in 6 orders of magnitude division. And then the gate signal needs to be 1 second or 1 millisecond. And so how do we get those signals? Well, the 1 hertz signal here, and 1 hertz is a waveform that looks like this, where the time from here to here, in other words the period, is 1 second. but you need a gate of 1 second, and the gate would be when this signal is high. Well, that's only half of a second, so that doesn't work. So there's this additional flip-flop there, which Heathkit chose to show with only 2 of its pins. I'm going to be preparing a new CAD-drawn diagram for this 1100. Basically, I'm just going to take my schematic for the 1101 and make some tweaks to it, but when I get that done, I'll be putting it up on the website. The description for this video will list the URL where that can be found whenever I get around to making that schematic. Hopefully not too long after making this video. Anyway, this flip-flop is connected as a divide by 2, so the signal coming out of here is half a hertz, which means that now it's 2 seconds, period, which means that the high time is 1 second, and that's what we want for the gate. This counter has 2 ranges, one in kilohertz, one in megahertz, and when we're in the kilohertz range, we do in fact want the gate to be 1 second long, so we get that gate signal here. But when we're in megahertz, the gate needs to be 1 millisecond long, and that comes from taking its signal from the 1 kilohertz signal. Well, the 1 kilohertz signal is like taking the 1 hertz signal here. It gives you a period that's wrong for the gate duration you want. So what they're actually doing is stealing it from the output of the first flip-flop in this IC, which, just like I mentioned earlier, is a divide by 2 flip-flop followed by 3 more flip-flops that together make a divide by 5. So they're taking that signal where the 500 hertz signal comes out and is wrapped around to get further divided, and they're using that, and that does in fact have a signal which is 1 millisecond long. So that's where that gate signal comes from. And now this is the gate signal. This set of gates here operating as inverters, they're all NAND gates, but when we have one input floating like that, the thing just acts like an inverter. And that is used to derive some of the other signals that are necessary for operation of the counter. The way that the counter works is you have the gate signal occurring every 2 seconds, and the gate signal is 1 second long, assuming you're in the 1 kilohertz range, and all the counting takes place during the gate. But during this period of time, also 1 second long, we do some other housekeeping chores. At the end of the count, when the gate closes, we have to copy all the counted data into memory or into some latches so that it will be preserved for display purposes. And after that, then we clear all the counters that would occur somewhere in here so that they're ready to count up again for the next reading. And then we do another gate up here. So that housekeeping stuff, we have the transfer, when we copy the data from the counters into the memory, and then the reset, which clears all the counters so that they can be used for the next count. So those things happen in here. And it's these gates over here that are developing those 2 signals. And they're using the gate signal, and they're also using 2 other frequency points as the actual 1 kilohertz signal and the actual 1 hertz signal. Not they're divided by 2 versions, but the actual 1 kilohertz and 1 hertz signals are also switch selected and get ANDed in with the gate signal, and then that produces For example, the clear signal or the reset signal for the counters, and over here it produces the transfer signal, which is used for all the latches, which is the memory. So once again, we have the gate, and when the gate is open for a very precisely generated period of time, then we have one decade counter. This is very much like what's inside of one of these, but it's actually built of 4 discrete flip-flops instead of having them all in one IC package. And that's because, at least at the time this product was made, the decade counters were not capable of dealing with high enough frequencies. But if you took the flip-flops, they were available in higher speed versions, and when you connect them together to make a decade counter, then that is capable of handling the higher frequency. But once it comes out of that decade counter, it's been divided by 10, then it's only 1/10 of the input frequency. It's no longer too high, and you can use regular decade counters, which are exactly the same kind as were used here. So we have 1, 2, 3, 4, 5 digits of resolution, 1, 2, 3, 4, 5 counters, 5 latches or memory devices, and again that's holding the count data while the counter is doing a new count. Otherwise you'd have the displays rippling. You could almost see it counting if the signal's low enough frequency. And then that data from the memory is always available to the decoder drivers, which take the BCD data, which is coming from the counters and has been kept in memory. That BCD data is decoded into one of 10, so whichever number we have from 0 to 9 has its own output on the IC, and those are connected directly to the Nixie tubes, and the common of the Nixie tube is from the approximately 100 volt power supply. So whichever BCD value is on here turns one of these 10 outputs on. The current from the high voltage supply goes through a current limiting resistor through whichever digit of the Nixie tube is appropriate, and then through the associated output on the decoder driver, and then to ground. So you have a circuit path, and that causes the one digit to light up. And the same thing occurs 5 times for the 5 Nixie tubes. There's a decimal point that's 2 digits from the right, and we're getting that by forcing on the decimal point of this particular Nixie tube. It doesn't move around on the display, it's always in that position. If the count is high enough that it exceeds the storage capability of, or the count capability of all 5 digits worth of the counters, then when its output turns on, that's essentially an overflow. It's saying we counted too high, and either the frequency is too high for this counter or we're in the wrong range. And we have to take note of that. So we have another flip-flop here, and that acts as a way of logging the fact that the most significant decade counter overflowed. And it's essentially just like the first flip-flop in one of these decade counters. It's just as if we put another decade counter out here, but only use the first flip-flop in it. So we're doing it this way. It's less expensive. And then you need to have it kept in memory. That 1 bit of overflow data needs to be kept in memory, just like this, but it's cheaper, instead of using a 4-bit memory latch IC, to use a cheapo quad NAND gate IC, and that's configured as a flip-flop that can store that data. If you just wanted to store it, you could use this simple set reset flip-flop here, but these 2 other NAND gates in front of it condition the inputs in such a way that you can, for example, conditionally reset it, and therefore not just reset it at any time. So it's a more sophisticated version of, it's actually a simple version of a flip-flop, but more sophisticated than just a simple set-reset flip-flop. The essence is it memorizes one bit of data representing the overflow, and in a sense there are 4 of those in these memory latches, 4 of these. The output turns on this transistor, which provides a current path from the high voltage supply for the overflow neon bulb, and that goes to ground. The 2 resistors here form a voltage divider because this Nixie tube doesn't need as much current or as much voltage to have an appropriate brightness as the Nixie tubes do. So to get it to look right, it has this voltage divider here. Alright, so the last thing to look at here is the front end circuit, which conditions the input signal so that it's appropriate to drive into the TTL logic devices. Keep in mind that we have a fairly wide range of voltages, signal shapes, frequencies, offsets. The signal may be a square wave, it may be a sine wave, it may be any kind of waveform. It may be very noisy, it may be very clean, it may be riding on a DC level and be all above ground. It may be a sine wave or an AC signal that is half above ground and half below ground. It may be all below ground. It could be all sorts of things. So the purpose of this circuit is to clean that up and make it a uniform circuit that is appropriate for what's downstream. So first thing we do is we come in the input jack and we get rid of any DC component or offset that there might be on the signal. And then we ground reference it or zero reference it with this resistor. So now the signal, regardless of what it was before, is now half above ground and half below ground, just like a good AC signal ought to be. The fact that this is a 1 mega ohm resistor sets the input impedance of this at 1 mega ohms. Then we have a current limiting resistor, fairly high value, 100K, and then 2 diodes to ground in inverse parallel orientation. These are going to be about 0.6 volts each to turn on. So if the signal gets more than 0.6 volts above ground, then this diode will turn on and essentially short out any excess voltage. And if the signal gets more than 0.6 volts below ground, then this diode will turn on and similarly prevent it from going further. So at this point now we have removed the DC component and we've limited the signal to plus and minus 6 volts. Now we have to have an input buffer, and that's made of the FET here, which has a very high input impedance and a low output impedance. And it's just set up as a simple amplifier, but not with very much gain. And the amount of gain it has is determined by these 2 potentiometers, the input coarse and the input fine. On the IB-1100, there was just a single potentiometer for this, and I think this coarse potentiometer was just a resistor and could not be adjusted. So here they have a couple of trim pots that you need to set for optimal sensitivity, and this bipolar transistor is connected across the FET to assist it in its operation. Well, now we've got a signal which has been made uniform as far as being above and below ground. And by the way, that can be level shifted somewhat by going through this stage. And it's been squared up quite a bit, but still not very clean. So we go it through an actual voltage amplifier here, boost it up a bit. Remember, there's not a lot of signal boost here. This is mostly an input buffer circuit. And then we have an isolator to isolate this stage from the following stages. Doesn't change the signal at all, it just buffers it. Then these two transistors here form a Schmitt trigger, and I go into considerable detail in my IB-1100 video on how that works, so I won't again go into it here, but it's essentially the same circuit. They left out a stabilizer that's down here on the 1101, so they cut a couple of corners in places where they felt they didn't really need it for this lower end product. But what the Schmitt trigger does is it takes whatever waveform you have coming in up to this point and makes it very abrupt, so you don't have any signals that go at angles or curves. By the time it comes out of the Schmitt trigger, it's either low or it's high, and the transitions are very vertical, nice square waveforms. And you need to have that if you're going to have a reliable frequency counter. And then finally, the signals here, the voltages still are not uniform, and they're definitely not the voltages that you need for going into some TTL logic. So this final transistor is there to assure that either the signal is at 0 volts or it's at 5 volts. So it's a level converter. And then we go straight from there into the first of the decade counters, as I've already discussed. And that is it. Once again, look at my video on the IB-1101 to get a more in-depth treatment of the circuit.